Hello. Today we're going to be looking at iodine trifluoride. So let's write down our molecule. Iodine trifluoride. Now we are going to be counting our valence electrons. So iodine has 7. Fluorine has 7. So fluorine has 7. And we have 3 fluorines. So 3 times 21, which 3 times 7, which equals 21. And then our total is 7 plus 21, 28 electrons. So our total electrons are 28. So now we're going to be drawing our Lewis dot diagram. So first we're going to be looking at iodine and fluorine. Iodine has a lower electronegativity. So iodine is going to be going in the middle. And then we have our fluorine, and fluorine. Now we are going to be looking at our bonds. We're going to be looking at our electrons, which is 28. We're going to be dispersing them around iodine to bond them with our 3 fluorines. So we've used up 6. And then next what we're going to do is 28 minus 6, we have 22 left over electrons. We're going to disperse them around our fluorine. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We have dispersed all our electrons around fluorines and our iodines. We've bonded them with our iodine, but we still have 4 leftover electrons because 22 is 24 minus 8, 28 is 4. So we're going to just draw in our lone pair electrons. So we have two of our lone pairs, and now we're going to be just counting our bonds. So let's see. Before we count our bonds, let's write this in a refined version. So we have fluorine, iodine. We're going to be drawing our sigma bond in green. 1, 2, 3 sigma bonds. Our etc. electrons around. And then we're going to be drawing our 2 lone pair electrons in dark blue. Okay, now we have a more refined version of our Lewis dot diagram. We are going to be counting number of electrons. Not number of electrons, sorry, we're going to be counting our number of bonds. So let's take a look. Sigma bond, we have 1, 2, 3, which is in green. So we have 3 sigma bonds. We don't have any pi bonds. We have 2 lone pairs. We're not going to be writing lone pair. For short form, we're just writing LP. And we have 2 lone pair bonds. Now we've listed our bonds, we've done most of the work, and now we're just going to be looking at geometry. So let's look at basic geometry at first. So basic geometry. Looking at basic geometry, we have 3 sigma bonds, 2 lone pairs. So that will be trigonal bipyramid. So our basic geometry is trigonal bipyramid. And next we're going to be looking at our molecular geometry. Molecular geometry. Our molecular geometry is T-shaped since we have two lone pairs. So let me write T-shape. Okay, so now we're going to be drawing our diagram, which is our VSEPR diagram. We'll draw that in orange. So, since it's called T-shape, it does look like a T. And we have our fluorine, our second fluorine, and our third fluorine. Now we're going to draw our iodine in the middle. And next we're going to draw in our bonds. We've drawn our bonds in and our iodine, and now we're going to draw our two lone pairs. Remember, we add some dimension. So by using these dashed lines, we'll be adding dimension. So that's our first set of lone pairs. And this is our second set of lone pairs. We're going to be using dashed lines and triangle to indicate dimension. Next, we are going to talk about bond angle. Our bond angle is just less than 90 degrees. So let's use green, bond angle. Bond angle. There. So our bond angle is less than 90 degrees. So our bond angle is placed right here. It's slightly less than 90 degrees. Slightly less than 90 degrees. So we don't use a L shape. We put a curl over there. So we have a VSEPR diagram and our bond angle right there. Next, we are going to be looking at our electron configuration. So our electron configuration, okay, so we're going to write over, what's the color that we didn't use? Okay, let's use pink. So for electron configuration, we have iodine in the middle, so we're going to be looking at iodine. Let's take a look. So we have 1s, 2, 2s2, 2p, 2, 3s, 2p6, sorry, 3s2, 3p6, 4s2, 3d10, 4p6. I'm just going to continue at the bottom because I don't have enough space. So 4p6, 4p6, 5s2. Next we have 4d10, 4d10, and last but not least we have 5p5. Okay, so this is the long version of our electron configuration. Now we're gonna write the shorthand notation, so let's write that in orange. Okay, so that will be iodine arrow, and we can refer to the periodic table. On the periodic table, the noble gas right before iodine is krypton. So we're going to add a square bracket, Kr, for krypton. Then this is 4p6 is where krypton ends. So we're gonna write the rest, 5s2, 4d10, 5p5. 5s2, 4d10, 5p5. Now we're going to be doing orbital diagrams. So for orbital diagrams, we're going to be drawing our boxes. So we're going to draw 5s2 and 5p5 first. So let's draw 5s2. And then above that, we're going to draw slightly bigger 1, 2, 5p5, and we have up, down, up, down, up, down, and up. Since we have 1, 2, 3, 4, 5. We don't have a 6th electron. Now we're just gonna draw 4d10. So 1, 2, 3, 4. This is our 4d10. Now we are going to be doing a process called electron energization. So to energize, we are going to be taking one electron from 5p5 and we're going to energize it or promote it to 5d10. So let's take one electron and put it there. The reason why we're doing this is because let's go back to our special types of bonds and how many bonds of each we have. So we look at sigma bonds and pi bonds. So since we don't have any pi bonds, we're going to be looking at our sigma bonds. We have 3 sigma bonds. Without the electron energization, just ignore this arrow, we will have only 1 sigma bond available. We can only do 1 sigma bond. Since we have more than 1 sigma bond, we are going to be moving this electron to the next electron level, which is 4d10. So we get a new diagram, which has so this is 5s2, 5p5, 4d10. Now we're going to draw in our electrons. Remember, we've moved this electron here, so we only have 1 here, only 1 here, only 1 here. So if you can connect, we have 1, 2, 3 sigma bonds, 1, 2, 3 sigma bonds, 1, 2 lone pairs. So this is all we need. We don't need all of this extra stuff. So what we're going to be doing is we're going to be hybridizing. So let's just draw a little dashed circle to identify our hybridization. And as you can see, since we have five slots, 5 slots, so 1, 2, 4, 5, 1, 2, 3, 4, 5 slots. It is going to be in S, P, 3, D, hybridization. So we're going to just transfer whatever we wrote here to here. 1, 2, 3, 4, 5, 6, 7. So now we have hybridized, and let's just go over, this is our last step, and let's just go over the process that I just explained. So we originally started off with iodine trifluoride. Iodine has 7, fluorine has 7. We have 3 of fluorine, so 3 times 7, 21 electrons. 7 plus 21, 28 total electrons. We drew our Lewis dot diagram. We first spread out 6 electrons to bond the fluorines with the iodine. Then we put the rest of the electrons around the fluorine, around each fluorine. We had 24 covered, we had 4 left over. We have 4 electrons and we put 2 lone pairs on the iodine. Then we just made a more simpler version to show our sigma bond. Let me just draw in that sigma bond. Sigma, sigma, sigma bond. And then we counted for 3 sigma bonds, 0 pi bonds, and 2 lone pairs. Then what we did, we looked at basic geometry. Since we have 3 sigma bonds, 2 lone pairs, it will be trigonal bipyramid. Since we have 2 lone pairs, we have molecular geometry as T-shape. Then we drew in our diagram, which has a bond angle of 90 degrees. Then we moved on to our electron configuration, 1s2, and we went all the way to 5p5. And then we wrote out a shorthand version, which is krypton 5s2, 4010, 5p5. Then we drew out the two boxes that we fill out, which is 5s2, 5p5. Then we need to energize to 5d10. And after we energize, we have 3 available for bonding. And then we hybridize because we don't need this extra stuff. We hybridized, and now we have an sp3d hybridization. Thank you.
Hi everyone, today we're going to be talking about nitrogen tribromide. So, let's start with how many valence electrons we have. Nitrogen will have 5 valence electrons. We have 3 bromine. Each bromine carries 7 electrons. That means we're going to have 21 electrons. 7 times 3 is 21, 26 with the 5. Okay, so let's look at the bond capacity. So nitrogen has a bond capacity of 3. Bromine has a bond capacity of 1. So since nitrogen has a bigger bond capacity, it's going to be our central atom. Let's start filling in our nitrogen. So nitrogen will have 5 electrons. Each bromine has 7 electrons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Bromine, 1, 2, 3, 4, 5, 6, 7. Great. Let's make this look a little nicer. Nitrogen. This is a covalent bond, so they'll be sharing their electrons. Bromine and 1 lone pair, 2 electrons. So our electron groups are going to consist of sigma bonds. So these are sigma bonds. And lone pairs. 1 lone pair. Let's label our sigma bonds. So, electron groups. We have 4 electron groups. Okay, and let's look at our basic geometry. We have 4 electron groups. That means we are going to have a tetrahedral. And looking at our molecular geometry, since there's a lone pair, this is going to be a trigonal pyramid. Okay. Let's draw our VSEPR diagram. So, nitrogen has one lone pair, one bromine. This is going to be on the other side, so we're going to draw one bromine here. And this is going to be behind. So we're going to draw it like this. And the bond angle is going to be 107 degrees. So we know our bond angle is going to equal 107 degrees. Now let's look at the electron configuration. So for nitrogen, we know that it has 7 electrons. So 1s2, 2s2, 2p3. So 2, 4, 5, 6, 7. Right? Let's look at the simpler version. We're going to do helium, 2s2, 2p3. So let's draw that out. How do we draw that? So for 2s2, 2s1, 2. Going in opposite directions. And then we're going to draw our 2p3. I'm going to draw them all in the same direction first. So 1, 2, 3. That's all we have. And then we're going to draw our hybridization. Same direction first. So 1, 2, 3. That's all we have. And then we're going to draw our hybridization. So what is that going to look like? 1, 2, 3, 4. So we're going to make 4 boxes here. 2, 3, 4. Okay, so we're going to move these here. 1 here, 1 here, 1 here. So what does that make this? This makes this an SP1, 2, 3. So SP1, 2, 3. SP3. Great. So now that we know it's an SP3 hybridization, we can draw our energy level diagram. So let's draw our energy level diagram right here. So right here. So energy here. Draw N here. N is equal to 1. N2 is going to be about half that distance. N is equal to 2. Okay. I'm just going to hold this. N is equal to 2. So we know that 1, 2. This is going to be our 1S2. This one, I'm going to do our 2S2. And then there, 1, 2, 3. This is going to be our 2P3. So 1, 2, 3. And there we have it. We got our Lewis diagram. We know our basic and molecular geometry with our VSEPR diagram. We got our electron configuration and our energy level diagram. Done.
Now, let's connect this back to grade 11 chemistry by looking at intermolecular forces, coordinate covalent bonds, resonance, and the properties of our 2 molecules.
Starting with nitrogen tribromide. Nitrogen tribromide's nitrogen forms 3 covalent bonds with bromine atoms. Nitrogen also has a lone pair, giving the molecule a trigonal pyramidal shape, which makes it polar. The intermolecular bonds are all regular covalent bonds, and there are no coordinate covalent bonds here. Between molecules, we have dipole-dipole forces and London dispersion forces. Also, nitrogen tribromide does not have any resonance structure because all the bonds are single and electrons are localized.
Now, for iodine trifluoride, iodine is bonded covalently to 3 fluorine atoms, and it also has 2 lone pairs. That gives it a T-shaped geometry, which is also polar. Again, the bonds are covalent, and between molecules, we have dipole-dipole interaction and London dispersion forces. There aren't any special coordinate covalent bonds or resonance here.
Comparing their properties, nitrogen tribromide is relatively unstable, a molecular solid at room temperature, and can decompose explosively. Its intermolecular forces are weaker than iodide trifluoride, giving it a lower melting point.
On the other hand, iodine trifluoride is more stable and has stronger intermolecular forces, mainly because fluorine is very electronegative, which makes the dipole stronger. That means iodine trifluoride would have higher melting points than nitrogen tribromide at room temperature. It usually exists as a solid and can submile.
So overall, both molecules are polar with covalent bonds inside. Neither has coordinate covalent bonds or resonance structures, but difference in electronegativity and atomic size affect their intermolecular forces, melting points, and states.